So I'm going to speak about mirror symmetry, but without really saying anything about mirror symmetry. So, in particular, the problem I'm going to address in my talk is the following one. So, given a polynomial defined in an isolated singularity, namely such that its critical set, that is just consists of one point, mirror symmetry associates to it B model. And well, that's well B model of mirror symmetry.
One point, you mean zero?
Yeah, indeed. So that's zero in Cn. So in general, one can assume a modular situation where this is just a set consisting of isolated points, but in my talk it will be just 1.0. So in particular, because in addition, I'm going to assume that this function f is quasi-homogeneous, namely that there is a bunch of numbers d1, dn, and df, all in that such that f of lambda 1 d1 x1, sorry, lambda dn xn is equal to lambda df f of x. So I will say that then these numbers define the weights of the variables x and also the weight of a polynomial. Namely, in other words, one can say that if one introduces the numbers d alpha by df, then this q alpha are now rational numbers, and they introduce the grading of the polynomial ring by the non-zero positive rational numbers. So in mirror symmetry,
But that's not enough. So the question is
Yeah.
not enough. The solution to this equation is just the only unique point of zero. Or
so
you get it automatically. I just don't understand.
not every function that satisfies the condition also satisfies that condition. But if you assume the function to be quite homogeneous, then you can say that you have just one singular point, just zero.
Isn't it the case of, say, monomial superpotential?
No, not necessarily monomial. Well,
If df equals 0, then
well, df is df is not.
Ah,
df is positive.
okay.
It's just a significant constant.
So,
So what is the typical example of such a?
well, there are many examples. So
Pick one.
the most typical is x1 to the power n plus 1. So
That corresponds to all requirements. For example, the monomial.
yeah, but usually it cannot consist of one monomial.
This one does not have unique critical point.
Sorry?
This function that you wrote does not have unique critical point. All, so
So, I mean,
If x1 equals 0, xa equals anything is
no,
also
well, here the number of variables is equal to 1.
okay.
Yeah, sorry, I didn't say so. Yeah, okay. So, well, n capital is equal to 1. And here n capital is equal to 3. Yeah, that's actually important. That's right. So, okay, and in mirror symmetry, to such a function, one associates a B model, and there are different ways how to associate a B model to such a polynomial. So I will call such a polynomial a quasi-homogeneous singularity. Even so, the singularity itself is not here. I mean, if one speaks indeed about the singularity, one should assume the variety f1 of epsilon for different epsilon in C. So, and then the singular fiber is over epsilon is equal to 0.
Will it be a definition, or will you also give a definition of what you call by being model?
Yeah, indeed. So, yes and no. The point is that there are at least two canonical ways how to construct a B model of such a fx. One more or less canonical way is used in homological mirror symmetry. And in that way, the B model is understood to be some derived category. And there are even different constructions that can be used. So different derived categories can be associated to the polynomial f. And then, in order to state mirror symmetry, one builds up a derived category on the A side and says that the mirror symmetry is established if there is an equivalence of categories. So the B model is a derived category, you can say it like that. Derived category now of a singularity of fx. And these are, for example, the so-called the category of matrix factorizations, or Orlov's category of singularity.
Excuse me, can you explain one unknown, at least one thing, so another unknown thing?
Yeah, okay. I'm going to stay away of that, so I'm going to formulate the problem. And then, and give you the definitions. And mirror symmetry is understood as an equivalence of categories. And there is another way how to formulate mirror symmetry, and then one associates to this function not a derived category, but this is more enumerated approach. Then one associates a homological field theory or in genus 0 and the Breuer-Frobenius management. So then, in order to say that the mirror symmetry holds, one should either build up an isomorphism of properties or the Breuer-Frobenius manifolds. But these are anyway some manifolds with additional data. And the problem is that mirror symmetry on these two languages is developed completely apart from each other. So, by different.
But again, as Anton said, you are trying to relate something partly known to him with something totally unknown to him, right? And whereas the definition, that's
So it will be on that like
much clearer. So basically, so you say that you have some mathematical space, you have some functions with these properties, and then you can take each of these functions and construct something in these homological terms is totally depressing me, because how this category depends on particular given function. So is it very much different for these two examples or not?
Yeah, it is. Those
Explain all these things on these examples. It would be best.
Well, Well, I'm not going to do that because I'm not going to speak about that. So the easiest way to say is that at least the category of matrix factorizations of F would be the matrices. So the objects of category of matrix factorizations of F would be the block diagonal matrices. I write it like this, I think. Yeah. So this is an object is O, yeah? So that O squared, oh yeah, I should write here, O squared is equal to F times identity matrix. So at least this I can get it.
So these matrices, they depend on your variables?
Yeah.
And in such a way that so F appears only in the right-hand side.
On the right-hand side. So, for example, in the case of the first polynomial, I think I can do that. So you can build up the objects that will be 2 by 2 matrices. x1 to the power k, x1 to the power n plus 1 minus k. K of them, k is equal from 1 to n plus 1. From 0, yeah, thanks. And, well, obviously, the square of it. Why not? But that's only the start, because I mean, these are the objects, you have to consider the morphism between them, so no one says that this should be 1 by 1 matrices. So,
and in order to do this, is it important that this function satisfies such a property?
yeah, so it's not really important right here to give such a definition. It's not important. But in order for this category to be, well, not too huge, so it is actually it is important in the same way as it is important that this ring is finite dimensional vector space. But because this is really the start. So,
sorry, MF, you understand it as a set, just a set.
well, I only said about the objects, yeah.
Okay, thanks.
But, well, to be precise, you have to assume two periodic complexes with the differential. Yeah, so this one acts on one side, on the two periodic, yeah, on the first and the second side. First and second vector spaces. So, and the problem is that, indeed, as said, different people use different definitions of mirror symmetry. They get results, but there is no way how to relate these results. Almost no way. So, still saying that there is equivalence of categories even of the same polynomial f means something about the isomorphism of the Frobenius manifold is completely unknown. So there are some constructions I will say, well, I will comment about them. So there are the ways how to build up these arrows. These are mostly by Barannikov, by Losik, also Shadrin, Haroshkin, and Markaryan. Junior one. Andrei Semyonovich. So, anyway, well, there are some ways how to build up some Frobenius manifold from a homological data, but well, one can construct something, but not say after that, well, how is it connected to the spring? Because there is no way to work with it after that. Okay, so what I'm going to do, I'm going to take some setup of homological algebra and construct out of it the Frobenius manifold. That's what I'm going to show. And also I will try to explain in the way why my construction is, well, better and correct.
And this is homological algebra, which you have also defined. So to construct it, you start with this, some of this function f. Yeah?
Yes, indeed.
And end up with the Frobenius manifold of p-type,
Well,
constructed with the help of this function.
so indeed my big big advantage of what I do will be that I indeed land in here, and this will be the Frobenius manifold of size theory, not some Frobenius manifold, but indeed of size theory. And well, the point is that this thing is not really unique. It depends on additional parameter, additional data, and I will hit that. So I will show how to control this additional data, how to work with it. So that's all. Well, so now we can get to the definitions. So our homological algebra setup will be about V algebras. These are due to Batalin and Wilkowitsky, at least named. So this is the following set of data. This is VD data, where V will be VD as a DG algebra. Namely, V will be an infinite dimensional C algebra with a product I will denote it just by dot graded in my talk, well, Z by Z to the grade. It will be okay for you. Graded, and D is a differential. So, okay, sorry, let it be Z graded. Yes, sorry. Z graded. So, namely, by Z graded means that V in Vn, and I assume the differential to be from Vm to Vm plus 1. And saying DG algebra means that D satisfies Leibniz rule. That will be this DAB plus this is, well, it's a gradient A. Yep.
A and B are elements
Of B. Yep.
And so what is algebraic operator?
So this is
multiplication.
yes, this is dot. This dot is the product of the
And graded means that the grade of the product is sum of the grades, yeah? Or something else.
Sorry, can you repeat?
Graded, so graded means that the grade of the product is sum of the grades.
Yeah, that's yeah. So the product, the product is also yeah. So and delta is a BV operator. Namely, this is some additional data. Delta is BV operator. It makes a DG algebra, a BV algebra. So, yeah. Well, saying the differential, I forgot to say that the square is equal to 0. Yeah, that's important. In here, in particular, that requires that delta square is equal to 0. And they compute with D in the following way. And next, well, D does not satisfy the Leibniz rule. Yeah, well, but is of order 2. 2 with respect to the product.
What is the degree of delta?
Well, the degree of delta, yeah. The degree of delta, yeah, delta lowers the degree.
By 1?
By 1. By 1. So I think actually this is not that important. This condition is not that important. So well it is usually used, but not really important. Yeah, that means, so this is something I don't really want to say. Well, that,
probably you would
Maybe by
get at least to be odd.
yeah, maybe. So, that means that in particular, if you try to play the same game with delta, it is non-zero. So, namely, if you can introduce the break, that is delta of A times B minus delta A B minus 1 to the A delta B. So this is non-zero. The first condition is non-zero. And the second, well, what is indeed equivalent to saying that for the two? And the second is that it is a break. It satisfies Jacobian.
So this is a requirement for this botanical constellation.
Yeah. That's the condition on delta. So
They want to be also non-degenerate.
non-degenerate. Yeah, I think. Well, actually, I think it follows from here.
Well, you can have Poisson.
Poisson and 12. Yeah.
Не, он мог бы быть, он не равновесен, он производные по части управления.
Да, я понимаю.
Нет, это
So-
неужизненность действительно дополнительная.
Yeah, I think, well,
Yeah.
I think here it's not important. Well, at least what I'm going to use. So in my case, so I will employ the particular BV algebra later on. For that, it will be I think it will be non-degenerate.
Is it sensible to ask what examples of this algebra
Yeah.
for these cases?
Yeah, I think so. Yeah, I think so. So actually, I hope everything I will construct today will be to take these categories, to take Hochschild cohomologies of them as a TG algebra, endow it with Con's differential, and then I think you will get exactly the same PV algebra I will be employing today. But well, I can prove it right now. So examples. Examples of such constructions, are the following. So if one considers the space of polar vector fields on CN, namely, well, on Cn, namely, that will be the direct sum I, G, where PV Ig will consist of all possible polynomials xx bar. Alpha is polynomial in both x and x bar. And here I, sorry, may I pick here?
Bar means complex GG.
Yeah. So I have q dx bars, and additionally I put here thetas q p. I will write thetas, but actually one can think of theta as d by dxk without the bar. So that's basically a letter that will make some formula easier. Obviously, one can associate to such an element a differential form that will send this to
This is like the dark water.
Yeah, that was space, right? Yeah, of harmonic forms, yeah. So right here I use both I and J forms. So I have Q non-holomorphic differentials, and both they holomorphic too. But well, the holomorphic now will be obtained by
you have
yeah.
the
Well, DN, yes.
if and this quasi-isomorphic sheaf of holomorphic vector.
Well, that's a tensor product of the space of sheaf of holomorphic vector fields by the by the anti-holomorphic forms.
Yeah, it's just all forms of text is zero Q kind of smooth coefficient. Sorry, but resolution of the sheaf of holomorphic.
So I don't know. Yeah, well, maybe I don't know.
Yeah.
So, well,
I have one more simple question, Roma.
yeah.
So this D and X, who is D and X?
The top form.
Top form,
The volume.
both from holomorphic and anti-holomorphic.
No, just the holomorphic.
Holomorphic.
Yeah.
So you act by this that, so basically, so that would be Q in dx bar and n minus p.
So Q is preserved. Q is here.
Q is point. I see. It's not product P times Q, yeah? It's n minus P, comma Q.
N minus P comma Q. Yeah, comma.
And then you just replace the rest by that.
Yeah. So I write here the volume form dnx, but actually one can take any volume form.
I see.
So
what?
and the point is that this space, has two differentials. Yeah, one is delta and delta bar. In here, both are both satisfy Leibniz rule. So both of order 1. But if you, well, this is an isomorphism. If you lift both to this space, then one of them is untouched. So, and therefore will satisfy Leibniz rule. But the second does not.
Yeah.
So now you can lift both in here. I will denote them by the same letter and just show how they act. So on PV we have delta bar that sends PQ plus 1, and this is just a sum of, well, okay, let me say how acts. May I say like that?
It's in a usual way.
In a usual way. So if this is omega, then this is a sum of k from 1 to n, d alpha by dx k bar, d bar k, and well, so we integrate dx bar. So then this is actually, one can depict it like this. Yeah? Take the derivative effect in alpha and also put the wedge. And what? Yeah, and d acts on omega in a more complicated way. This is the sum of d by d xk, d by d theta k. And this is d alpha by d xk, holomorphic. And next, one should apply, well, I can write like this. I have these wedges, and therefore everything is anti-commutative. So the d theta are also anti-commutative. So it hits one of the elements out of here. If it doesn't hit, then it is 0. So that's a fast answer to the question, what does it mean to be orthogonal? It differentiates twice.
Is it delta or
This is D.
D? Yeah. How is it related to that?
The space PV, comma D, comma D bar, comma D is a PV algebra.
Yeah.
So it is obvious that they square to 0. It is obvious that they anti-commute. So PV d bar D is an example of PV algebra. So with this being differential and this being BV operator. A bit unusual, but
The algebra you denoted by A is also an example.
well, if you introduce the BV operator in the operator.
Multiplication.
Well, I didn't say about the product. The product is, component-wise.
These are the multiplication.
Yeah, okay.
And then it is the algebra to PV. It will not be anything.
Okay. No, I don't
Because the standard multiplication D without bar is the first order operator.
Indeed, yeah. So that's the point. Yeah. Mhm.
And you say that the multiplication is just multiplier.
So you multiply the polynomials as the polynomials, and then on each tensor factors you take the wedge product. But well, of course, one can respect all this, the signs.
In this your picture example, there is no room for function f.
Right. So now I have to add up here a function f. Recall I had this polynomial f, and it was indeed only in the variables x. So, and now I construct new differential. I will construct a BV algebra, and a little bit surprising will be that I will change the differential and not change the BV operator. So this will be BV algebra on the same space with a new differential, and the differential will be this. That one. That one. Over here.
With D instead of delta.
With D instead of delta. Actually, well, this is in words, so I can basically write how it acts. It acts as follows. Let omega be as above. So then this is a sum from k to n multiplied by the derivative of f. Take d by dtk, well, and all this to alpha, t to k. So in particular, that means that, so this is now equal to k from 1 to n, df dxk multiply alpha x bar. So alpha x bar is not touched. You just multiply it by derivative of f. So then minus 1 to the power q delta of dx bar times d by dtk applied to delta of tj.
But we will give grading.
The grade, yeah, I think so. That's why I didn't want to really say that delta should be low in the gradient. Or maybe yes or no. So the point is, I have here the by gradient. Yep. I didn't say what is PVN. So I have to think a little bit, but I can say that PVN is equal to sum of PVI plus j or to sum of PVI minus j. So so what is better? Both better?
But F is not homogeneous.
So what?
F itself quasi-homogeneous.
Quasi-homogeneous, but that's not quasi-homogeneity. That's quasi-homogeneity of this alpha multiple, and it's not considered in here. So in principle, this is not important. Because usually the reason why people try to work with such deltas are that it helps consider the equihomology. In my case, it's not that important. I can actually explain why. The point is,
so this is the definition of the bracket, and so the derivative is all derivative, all anti-holomorphic derivative plus what's written here.
yeah. So then indeed, the problem is that in particular, if you apply d bar f, then this d bar raises this part by 1, but this field lowers this part by 1. So therefore, indeed, so with the gradient of the differential, it's a little bit better.
But it says G2 to be.
Yes, that's true. That's true. In my case, well, it's not really important for me because of the following.
Why don't you use degree?
Don't I use whom?
Degree.
Well, well, the point is that these two are both differentials. I mean that d bar. Where did? Yeah.
Is it correct that in the picture is algebra A?
Yeah.
This d bar f is just d bar plus df.
Yeah. Yeah, that's true. Yeah, that's true. So the point is the following: that this is equal to 0, and actually d bar and bracket f commute.
But in that picture it's not.
Yeah. In this two. Well,
Yes.
okay. So all this. Well.
I think it also means this bracket is 0.
Well, the operation of taking bracket with f
Twice. You play it twice.
applied twice
Something
as say, well, df squared is equal to u.
in particular, so it would be Jacobi identity. Well, there is no Jacobi identity.
Well, the Jacobi identity is with Jacobi identity. Well, yeah, maybe from that one. I don't know. I mean, in this case, it's basically easier to take it by to check it by hands. Well, we can change it.
Okay.
So, and therefore, the homology of PV with respect to d bar f is first of all isomorphic to cohomology of this. Well, I mean, you mod out all the anti-holomorphic parts. So this cohomology is.
You mean that you assume that d-bar cohomology vanish in degree greater than 0?
Yeah. So and then you have a cohomology of the following complex. So this is Cx. I mean, in all the variables. X1, Xn. Here is, well, dk theta j.
In the right-hand side, I don't want to take the holomorphic.
Yeah, holomorphic indeed. So indeed holomorphic polyvector fields.
Yeah.
Holomorphic, only holomorphic coefficients.
Because this is not invisible from
Not dependent on the x bar.
From your notation. You will see star 0.
Well, you take you have only the polynomials alpha dependent on x, 0 form in here, and any number of vertices.
This is not what we're doing. TV shall
Yeah, that's true. That's not a problem. The notation is well, yeah. So, well, I can continue like this. So this is homology of this complex. So where I don't have any d-bar part now, and this is actually the factor of the polynomial ring by the ideal generated by the derivatives as a vector space. Yeah, as a vector space.
Because the instruction, the right-hand side is agrees with A, not with CD.
What is with A?
The algebra A,
Yeah.
which is as a vector space, is differential. Is isomorphic to DB, but different.
Well, but anyway,
different multiplications, right?
I take my product on here. So I take my product on here.
Yeah, but this isomorphism is not an isomorphism of
I think it is.
Because the right-hand side is clearly the quotient is obtained as the quotient beginning from the lower picture with A.
Yeah. Well, no,
It's just multiplication is df.
Yes, that's true.
So by definition, you
Yes, that's
the
true.
right-hand side there is. Maybe on cohomology the multiplication is specified. Another one which is on the which is manifested on the left hand side, right?
What would it be? What else is it?
If you have to we have two complexes. By the way, the differential in the lower picture is a zero-order operator with respect to multiplication, and in the upper picture is the first-order.
You mean in which upper and lower?
But I don't know. Maybe the
No, which operators?
Huh?
Which operators? So indeed, well,
No, еще
I'm not sure I can translate correctly in here.
Вот
Да.
ПВ-картине,
Да,
значит, ПВ-картине А-картина.
да. Вот давайте будем про...
Как версия векторных пространств, они изоморфны.
Ну да, хорошо.
Но имеют разные умножения.
Да.
Так что один и тот же дифференциал в верхней картине ПВ. Это оператор первого порядка.
Да.
Вот этот вот.
Дебат.
Скобочка Ну, мы уже перешли после того, как D-щепсой убрали, осталось скобочка да?
Да.
Вот. А в нижней картине это умножение на D.
Да.
То есть нулевого порядка. Это показывает, что умножение действительно разное.
Хорошо.
Так? Значит, космология в картине с буквой А это буквально вот то, что написано на правой стороне. Факторизация по образу умножения на D.
Ну, дело в том, что просто, well, the point is that this isomorphism is given basically as follows. So the class in here, that is a class of some polynomial in X, is sent to that cohomology of full PV with d bar f to an element phi of x, and here I have 1, 1. Meaning that 0 hatch here and 0 hatch here. So, well, and the product is the same. Because the product of the classes here is a class of product, and here too. Well,
Could be. Maybe on the homology the two things are the same.
so,
That is probably crucial because I believe that the problem on the right hand side will be the same as problem in the drawing from the
well, at the origin of that. At the origin of that. So that's the product at the origin of a Brownian indeed. So now what we're going to do is to construct a genus zero coefficient data from a BV algebra. So this is now construction of Koroshkin, Markaryan, and Shadrin, whom I quoted at the start, who say that if you have a BV algebra but with some additional data. They denoted by this, saying that BV algebra plus delta resolution. That means that they have a series of operators such that the following identity holds, such that it should be assumed now as a map from the complex V, comma D. Well, V, comma D, maybe. With a new differential, d bar f plus z delta. And then this equality says that it sets up quasi-isomorphism.
So in the left, the differential is d bar.
Yes. Ah, well, yeah, I wrote it. Yeah. So let me. So it was this, yeah. So then to this data that is now V, D, delta, and psi.
And the second line is also D instead of double.
Yes. Thanks.
What would be an example?
Well, example will be so example of a delta resolution, yeah? I will give an example. Well, let's give a simple example. Well, the simple example will be of our DG, of our PV algebra. Where of such a BV algebra. So let's fix some generators. Well, some polynomials. Phi1, phi mu. Okay, let it be. Let it be n is equal to 1. Yeah. Okay. N is equal to 1. It will be basically easier. N is equal to 1, and f is x1 to the power m plus 1. Yep. Then I want to construct such a map. So it should be a linear map, and I will construct it from V in here to V CZ. So what will be my V in here? V.
That's not a map you need.
It's not unique. So
it's not a map you need, because you have something different. You have to add ZD to D bar.
Commuting with the multiplication by Z on the left hand side.
So now you just sort of introduce Z. Okay.
So also, well, that was V in there, yeah. Well, but this is PV, yeah. Because n capital is equal to 1, my PV consists of the polynomials xx bar 1 times 1, 0's wedge, plus polynomials xx bar dx bar 1 times 1, plus alpha xx bar, well, 1 times theta 1, plus alpha xx bar dx 1 bar theta 1.
But we have to write ones because arguments of alphas
Okay.
are the same length as without one.
Okay. Well, I don't mind. So now, because I only need an example, I will take my map theta. So, or C, yeah? That's an ansatz for my construction that psi commutes with d bar. First of all, and second is that psi commutes with multiplication by x bar. Well, and okay, then also with the x bar. So I'm going to define psi. Define psi only on C Moreover, I want this psi to act trivially on homology. To do that,
How this is first equality is consistent with this psi of d, psi d is equal to d plus z.
very easy. I mean that what I want is that psi d plus bracket f is equal to d bar plus bracket f plus z d psi. So this equality reduces my problem to psi bracket f is equal to bracket f plus zd psi. So, and then I take the following. Well, what is my cohomology? Cohomology of the DG algebra, I mean of PV with d bar f, is isomorphic to the Jacobi algebra of f. Jacobi algebra of f is a very simple thing. As a vector space, it is generated by the classes of the polynomials 1, x to the power n minus 1. No.
Xl is equal to 0.
So, and out of this, I fix the polynomials whose classes generate this judge, and I say that I represent Cx, the polynomial ring in one variable, as an infinite dimensional vector space with a basis f prime to the power k and x to the power l, where l runs from 1 to n minus 1 and k from 0 to infinity.
So what is the sense of this equality? That's, you just represent your C of x
Yeah.
in that way, yes?
Yeah, the point is, well, that's actually what you need, because, well, this, let's have a look at this equality at the start. Well, what does star mean? Let's apply it to what? If I apply it to an element from here, I get 0 on both sides. Let's apply it to an element of here.
Why you get 0 on both sides?
Well, yeah, sorry, maybe, well, I will be also using this. Yeah, I think so. So let's apply it to this reason, because it's anyway more important. This applied to alpha x 1 then the theta, so it should be equal to f plus z d psi of alpha x 1 theta. So what is this? This is actually psi applied to f prime alpha x 1 times 1.
So that you apply this bracket to...
Yeah, bracket it. So multiply by the derivative and take d by dt. So what I have on the right hand side, as I said, I basically define psi only acting on the C of x. So this will be bracket f plus zd C of alpha 1 times theta, and this is equal to C of alpha multiplied by f prime plus z plus z. Sorry, sorry, this. It should be P of alpha psi alpha plus z d. Well, okay, this is just P alpha prime 1 times 1.
Who's C for prime?
Derivative with respect to the variable x.
Where from it? Where there was something like derivative d, which is
Yeah. So my d.
your d, yeah. The d is this.
So d was this.
D from the theta. I see. So it removes
Oh no, this, yeah, this.
it removes that which you have,
And puts one, yeah. So actually, in order to meet that condition, all you need now is the following. It's enough to have that psi of f prime alpha of x is equal to f prime psi of alpha plus z psi of alpha prime. Now take psi of f prime to the power 0, that k is equal to 0 on the left hand side, xl to be to act identically. And this formula allows one to build up all the higher psi of phi alpha, phi prime, psi of f prime alpha k out of the action of psi on the generators of the Jacobi ring. So if one writes this as phi alpha plus z d by dx applied to psi alpha, then this says that psi of psi prime to the power k xl is equal to f prime plus z d by dx to the power k applied to psi of x alpha, that is x alpha. Oh, sorry, x alpha. So the point is that one can play the same game not only with number of variables equal to 1. So in this case, one indeed needs to construct a C-infinity vector space basis of the polynomial ring. In one variable, this is sort of easy because one can divide by f prime, that is a polynomial of order n. So in one variable, the polynomial division algorithm works unambiguously. In many variables, not. But in many variables, one can fix anyway the monomials generating the basis of the Milnor of the Jacobian algebra, and then such a basis is anyway possible. So that was an example.
I have a specific question. If you the data doesn't have a Jacobi,
No, it doesn't.
It's not satisfied by this possible.
No, I think it doesn't. It doesn't because delta does not satisfy.
It has both so right and over theta.
So the right-hand side is not really algebra.
You mean here?
Yes, on the right.
In here, one even doesn't speak about the BV algebra. In this map, that's a map of the DG algebras. So the only thing that is important here is about homology.
Do we need for DG algebra desatisfy Leibniz?
Yeah, we do. So okay, yeah, maybe. Yeah, maybe I didn't.
So what Vadim says is delta resolution does not map your algebra So resolve the algebra into anything reasonable.
Yes, that's a good point. I mean, that's a quasi isomorphism of the complexes, not of the DG algebras, because the square is anyway zero. That's okay. And in here, one doesn't impose any condition on the product, so it's enough that psi should be just the map of complexes. It should not respect the product. So how to build up any de Broglie-Frobenius manifold out of this?
This your equation reminds a little bit of the Broglie's dependent connection.
Well,
Uses some descendants out of. But okay, give an answer. Also, I'm very sorry, you have not yet defined what is the Broglie-Frobenius manifold.
No, да.
I know that this is just a Euclidean space with one distinguished direction. But maybe you need another definition.
The zero vector. Distinction direction. Yeah, okay. I was going to give another definition. Why is the size here? Well, assume more than Koroshkin and Markarian wanted. Assume that homology of VD has a pair. They don't need it, but anyway. And this is a Frobenius algebra. So in particular, that means that eta of AB from the homology is equal to eta 1 A multiplied by B. Then consider the graphs. We're going to introduce the phi alpha 1, tau phi alpha n minus 1. And I only put a semicolon here, tau phi alpha n, depending on that psi, depending on the resolution. And I will call them the correlators, G0 correlators of BV with resolved delta.
Who are phase?
Yeah, good point. Good point. And the homology of VD is a C vector space spanned by these phi's.
So in your example, these go from 1 to minus 1.
Yeah, those classes indeed.
And who is tau?
Tau is a Steve
Can you just remove it?
these are just tau 0. Okay, let's remove them. The point is that these are tau 0 and
Fine. So one is distinguished somehow.
yeah, unfortunately, yeah. So
And what is the subscript n?
because I have n of them.
It's already clear without.
Well, it's already clear.
Less letters is always better than more letters.
So I do the following. I consider the trees, rooted trees.
But again, Sergej, when you say correlators of BV delta, it doesn't mean anything, right?
Well, to some extent.
It's some map to numbers from somewhere, but you have not also defined it.
Well, in my example, they will turn out to be relators of the De Bruijn-Frobenius manifold.
Yeah, but you need, by now,
Yeah.
once we don't know what is the Frobenius manifold,
Yeah.
you have to say something about these numbers, having at hands only this BV algebra. That's right now it's completely unclear.
In terms of the BV algebra, they don't
Don't have
any explanation with relators.
But do they exist? If you just have this BV algebra,
Yeah.
you don't have any functions, any numbers, right?
No.
So you just have some algebraic structure.
Yeah, that's
Now you
that's
want to find some numbers
Yeah.
and relate them to this algebra. In which
And relate them. Well, that was all about the homological world. This was all from the homological world.
Okay, and then what will be the any relationship between your homological world and the Frobenius world?
That these numbers will be exactly the correlators of genus 0 for T.
Yeah, for that you don't need anything homological, right? You just say that they are somehow defined in the Frobenius world, and
No, they will land up in the De Bruijn-Frobenius world. Right now, we have started with the homological data, and also Psi. Psi is homological data.
C is homological data, and this phi is homological data.
Yeah. Because well, they generate the homology.
But will they give the definition of these numbers in terms of some homological data?
Yes. That's actually one of the problems with this Psi, because these numbers, they depend only on cohomology. These phi's are generators of cohomology, but psi should anyway be defined on all the complexes. So consider gamma to be root of trees. So I consider all the rooted trees with n minus 1 inputs and root being the output. So additionally we number the inputs in all the possible ways in -1, and we associate to a root the operator psi of minus z, and to input psi is 1. To input psi of z, and to edge one should associate the operator that is 1 minus root is this psi 1 of minus z psi of w by z plus w. So I didn't say about z. Also to any input gets its own zk. So formal variable that is associated to every input. So I have here z1, z2, z3, z4, z5, z6, zn minus 1, and also the output gets its own variable zn. So when I associate to a root or any input psi, that means that this gets psi zn and this zk with its own variable. Also, on every edge consists of two half edges. Every half edge gets its own variable. Let them be w and z. Then this edge operator is exactly in this variable.
So altogether, the whole picture depends on n variables of input and output and extra pairs.
Twice number of the edges.
Twice number of the edges.
So now to every such graph, I can feed now these elements of the homology. So I feed phi's to the inputs and the last phi alpha n plus 1 to the output. After that, I construct a number. I should construct a number out of that. The number is constructed as follows. At every vertex, one has to consider the product. The homology product. So I first start at the inputs. I construct here, I compute here a product. It gives me an element of cohomology ring multiplied by these z's to different powers. I give it further to the next vertex. Once again, I multiply. I get once again an element of cohomology ring multiplied by the bunch of z's. So finally, I get an element of cohomology ring of Vd multiplied by some z's.
It's for every tree, yes.
It's for every tree, yeah. So now you should consider these z's as the psi classes in the modular space of curves and integrate. So finally, our goal is to get rid of this part, and one gets rid of this by assuming the following map. That one to the k, map to c, by that I to the power di sent to the product over m from 0 n of psi I to the power di. So in other words, this is n minus 3 n minus 1 by the product di if sum of di's is equal to n minus 3 and 0 otherwise.
Is some sort of selection rule for these trees, or
Yeah. For example, one can check that for this psi that I have constructed here, because its action on the homology ring is trivial, so if psi on homology is equal to identity, then it follows that the edge operator is basically 0. So, and as it is 0, we only have the one vertex graphs to which we can associate n-1 input and output. But the point is that we should anyway consider that operation. And this operation says that if the numbers of these, namely, after all, we will finally compute this map with all the d's equal to 0. And that means that this final operation will anyway give something. But this final operation, well, let it be double star. So, and double star is non-zero only if n is equal to 3. And in that n is equal to 3 case, it will give just a product of two elements given here and send that.
So that corresponds to multiplication.
Yeah.
That 1 times 2
Yeah.
equals to 3 as multiplication.
Yeah. If one finally, well, I say that we have a pairing. If one finally takes the pairing of it with 1, that will be exactly the related to topological field theory. Topological field theory of this algorithm. So, well, that's actually the stuff. Well, I mean, yeah.
That would be a good probably point to start our nervous system, yeah? But we're now clearly over.
Yeah. I think so. Yeah.
Questions? Do you recognize anything? But в конце можно заметить.
Ну, в конце, да.
Таким способом. Вадим, а вас сейчас еще будем что-нибудь придете.
And ambiguity in the name of C is not important yet.
Well, it will give different numbers finally. So the correlators will depend on this ambiguity.
But what does that mean? Is it control?
It's very good that we have this ambiguity. Because I said to them at the beginning that there is some ambiguity for the Frobenius side. So this ambiguity will be controlled by this ambiguity of psi. But anyway, it will be important on homology. And before that, on the complexes, it will be even not important. I mean, it will be even more.
Знаете, как Саша в конце все нет. Мой Саша считает это может подтвердить это. Спасибо.
The evolution, I don't know. I'm not sure. I don't know. Symmetry. So here now.
But you have this additional structure here. How would you formulate this here? What do you expect from any sense?
I expect.
Oh, this should be like in general, the compares to two-dimensional topological field theories in the sense that users to take some sort of option homology or co-homology this additional structure. And you say that, in fact, it's not sufficient to consider only Frobenius manifold. To say that it means this additional probably input in the form of this delta resolution.
So the delta resolution is exactly to construct this Frobenius manifold. So without it, you only have the algebra structure, and that's all. And the point is that the algebra structure is just very little amount of data. So exactly, the delta resolution is something that you need in order to get non-trivial relations.
You mean non-trivial trees?
Non-trivial trees, and out of them
But I would write that this delta resolution need to also include these descendants into the Breuer's picture, because just what I thought, the Breuer-Frobenius manifold is not finite dimensional.
Yeah.
It just only say you picture the dimension corresponds to the dimension of homology of something. Yeah?
That's true, yes, the dimension corresponds to it, yeah.
And just without, as you said, the M.
Yeah.
Maybe not. Because here you say that if you call this sum to zero, you end up only with a three-point function.
Yeah, but that's actually important thing, because the primary question is if this BB algebra is in total resolvable, if one can resolve it. And it's, well, after you have constructed the resolution that acts trivially, you can add up some operator that only acts on these phi's and acts trivially on everything else. So we had this product, f prime multiplied by x to some power. You take the operator that acts on this x to some power and trivially on this f prime. Then you can get, well, more and more resolutions, and that will act as you want on cohomology. But the primary question is indeed to construct some resolution.
Спасибо.